Hi, I'm Matti Lehtinen from Karolinska Institute and University of Tampere. And today I'm going to talk about HPV type replacement following vaccination. And why this is important and timely is that we now have HPV vaccination programs launched in several countries, and if anything, we should be monitoring the HPV type replacement because type replacement following vaccination has been the reality following pneumococcal vaccination, and actually following the modeling work of Mark Lipschitz, who predicted that type replacement against a few serotypes covered by vaccine would follow with non-vaccine covered type. And really, this has happened following pneumococcal vaccination, but whether this is true for human papillomavirus vaccination is the topic of today. Type replacement it's a question of definition. Type replacement may follow also population mixing. This is what happened in the late 80s, early 90s, following the breakdown of Soviet Union and opening of the border between Finland and Russia. We were experiencing a lot of influx from Russia, and this did not go without consequences. The number of immigrants was increasing from Russia, and they came also with new types of sexually transmitted infections. The type distribution of chlamydia trachomatis was changing in the 1990s and then returned back after plateauing of the immigration in the 2000s. And this is kind of an indication that mixture of populations can result in changes in the type distribution of at least sexually transmitted microorganisms. So what we did in Finland at the population level was a community randomized trial on HPV vaccination, comparing different vaccination strategies, gender neutral in Arm A communities and girls only in Arm B communities, and comparison was, of course, against control communities which were receiving hepatitis B vaccination. And this was with moderate coverage in early adolescent girls born 92 to 95, and early adolescent boys in the gender neutral arm communities of similar age. And we were comparing vaccine efficacy, herd effect in the unvaccinated, but also overall impact of vaccination strategy by weighing the vaccine efficacy and herd efficacy by vaccination coverage. So this was done in 33 communities that were randomized, and the heterogeneity between the communities was reduced by taking into the different arms for randomized randomization strata of high prevalence, intermediate prevalence, and low HPV 16-18 prevalence communities. And so this was working pretty well in the when we were looking for the herd effect against HPV types 18, 31, 33, which all have relatively low reproduction rate. The herd effect was statistically significant in the gender-neutral arm communities, and this was different from the girls-only communities or control communities. And as for HPV 16, we could observe this also for HPV 16 using different approach. Instead of the PCR prevalence, we were looking for seroprevalence in the vaccinated cohorts, and with the comparison of HPV 16 seroprevalence in Arm A communities against the pre-vaccination situation, we could demonstrate that actually also HPV 16 seroprevalence was reduced, but only in the gender-neutral communities, which was an indication of the superb herd effect that was gained in the gender-neutral communities. And of course, this we have then been monitoring further with higher vaccination coverages and using the THL Simo-Pekka model on the on the reduction of HPV prevalence, which with on the right with the gender-neutral vaccination with 75% coverage is leading to complete eradication of 16 type in 30 years. And this is sort of the basis for the gender-neutral vaccination strategy being used in the vaccination program. The flip side of this, of course, is that the ecological niche removing HPV type 16-18 from the adolescent populations onwards is taking place, and this is a starting point to look for the prevalence ratios, pre and post-vaccination prevalence ratios in an arm-wise fashion in the vaccination communities, looking for what happens to the HPV types. The study baseline is the individuals who were vaccinated as early adolescents and attended a re-randomized screening study at age 18 in consecutive years, and provided information for HPV type distribution in cytological samples that were obtained from these individuals at ages 18, 22, 25, and 28. And the compliance of this study, still ongoing, has been very good, so that 93% of the initial study participants have been participating also at visits 25 and 28 years of age. We have used high throughput PCR methodology for looking at different HPV types in the obtained cervical samples. Kind of reminiscent to the chlamydia observations in the past for ranked order of different HPV types. We were looking for possibilities to see differences between vaccination arms in the ranked order of non-vaccine HPV types. However, there were no differences between vaccination communities or control communities with regard to the ranked order of HPV type prevalence. We were looking also for non-vaccine HPV types 39, 51, 52 that were not covered with the vaccination, and looking both for vaccinated and unvaccinated populations. We did not see any differences in the prevalence ratios, even in the first vaccinated 2 birth cohorts compared to the 94, 95 birth cohorts vaccinated later. We were also looking for the core group of sexual risk-taking behavior. We were looking for chlamydia trachomatis positive individuals and the possible changes in these. There were occasional changes. 51 type appeared to be somewhat higher, but this was not consistent over the consecutive birth cohorts. And this was also true for the non-vaccinated individuals compared to the control communities. So the next thing was that we were looking for seroprevalence differences, again pre-vaccination seroprevalence and post-vaccination seroprevalence for a number of HPV types in the serum samples obtained from pregnant females who had donated a blood sample to the Finnish maternity cohort by age 22. And the vaccination coverage by communities where these women were residing was in the RA, that is gender-neutral vaccination communities, close to 30% in the post-vaccination era, and a little lower in the girls-only vaccination communities, and negligible in the control communities, and of course in the pre-vaccination era. So the serology was able to detect serum antibodies to 17 different HPV types, and we were using herpes simplex virus type 2, the cause of genital herpes, as a surrogate of sexual risk-taking behavior. We were looking in this core group of HSV2 seropositive individuals, these seroprevalence ratios for the non-vaccine HPV types, but didn't observe any consistent differences suggesting increased post-vaccination seroprevalence for non-vaccine HPV types. And there was only one HPV type 68 that showed in the girls only vaccination arm statistically significant increase in the seroprevalence post-vaccination, but making many comparisons for many HPV types between 3 different study arms, one would expect by chance 1 or 2 significant findings. This was not consistent with PCR findings. So we did not observe arm-specific changes in the ranked order of HPV types. We observed only sporadic inconsistent changes, increases in HPV 31, 38, 39, 51, 52 prevalence ratios, and the HPV 68 prevalence ratio increase was the only observed exception from the kind of solid pattern. The lack of these epidemiological observations during the first 8 years post-vaccination was no wonder, because the honeymoon period, when according to mathematical models it is expected that non-vaccine types are taking over from the vaccination-covered HPV types, is actually starting 10 years after vaccination, and we were perhaps too early with our epidemiological studies. There has been one report from the Netherlands about increase of non-vaccine HPV types in following vaccination close to 10 years from the start of vaccination program, but still this is the only report so far from the epidemiological approaches. So what to do? We had this ecological niche starting to be cleared from HPV type 16-18 by the gender-neutral vaccination that we implemented in 11 communities. What to do? What was the next approach? Was an ecological one, looking for the type distribution in these communities, and it was clear that in the control communities, the 16, 18, 31, 45 types were the predominant type and clearly differentially distributed than the non-vaccine HPV types or non-vaccine covered HPV types in the gender-neutral or girls-only arm. And this was an ecological approach that was looking for the heterogeneity between the girls-only arm, gender-neutral arm, and the control arm. And the greatest diversity was observed in the control arm, arm C, where hepatitis B vaccination was used. But what was notable was that 8 years post-vaccination, the diversity of HPV types was back in the gender-neutral arm communities. It had regained the diversity in spite of the fact that HPV 16, 18 were removed from this. So a new set of type distribution was materializing in the gender-neutral arm communities. The diversity remained reduced in the girls-only communities. So the niche occupation, that's the bottom line, by HPV types 35, 51, 52, and so on, was observed in the gender-neutral communities, and this brings us to the question of what do we mean by type replacement? Does changing ecological diversity equal type replacement? And this is how far we are at the moment. It's sort of a continuing study. We have samples not only from the first 8 years of individuals post-vaccination, but also from individuals up to 16 years, 16 years post-vaccination, and we are looking for the ecological diversity in these arm-wise samples that are available. Thank you.